and skew-symmetric matrix. What do you mean by symmetric matrix? So for example, let me take a matrix and see its transpose. Let me choose a matrix in such a way that say this is 2 and 2, and let this be 3, let this be 3. Okay, now let's take its transpose. Transpose will be 2, 3, 3, 2. So do you see any changes in this? Don't you see A is equal to A transpose? Yes, such a matrix are called symmetric matrix. Okay, so can you expect the same in a non-square matrix? So for example, 1, 2, 3. Obviously, it's a column matrix. And when you take a transpose, it will not be equal at all because it becomes a row matrix. So not just this, if there's a 2 cross 3 matrix, when you take the transpose, it will become 3 cross 2 matrix. So this will never be equal, right? That is why a symmetric matrix must be what then? Symmetric matrix must be a what matrix? It has to be a square matrix. Okay, then the diagonal elements will not be affected. You only change the other elements, right? One more example will give you 1, 2, 3. I'm going to be careful while writing this. Here I'm going to have 1, maybe you can have any number here. This doesn't matter. And whatever you write here, I have to write here only. So now this is a square matrix. What is its transpose? Its transpose is 1, 2, 3, 2, 4, 7, 3, 7, 5. This is again same. So those two are equal to each other. Again, it's a square matrix. That matrix order should be same. Then, I mean, both rows and columns should be equal. Then only we can have a symmetricity, right? That's why symmetricity exists. A symmetric matrix are possible only for what kind of matrix? First learning, square matrix. Then what is skew-symmetric matrix? Let's see. What is skew-symmetric matrix? It has to be somewhere related to symmetric matrix, right? So what is skew-symmetric? It's explained here. A matrix is said to be skew-symmetric if transpose is equal to negation of the given matrix. There's an example here. See, a matrix is here, B, and its transpose is here. And we are writing 0, 2, 4 in the row wise. Here, right, they're writing 0, 2, 4 in the column wise. So next, minus 2, 0, 3, minus 2, 0, 3, minus 4, 3, 0. This becomes minus 4, 3, 0. So these two are not exactly equal, but when you multiply this with a negative sign, it will become again 0, minus 2, minus 4, 2, 0, minus 3, 4, 3, 0. After multiplying by that, right? So this is actually negative transpose of the B, right? That's why it becomes skew-symmetric matrix. But one observation here also we have square matrix only, right? Another important observation is if a matrix is skew-symmetric, the diagonal element should not be changing, right? So when you change the sign also, it should not change. That means the diagonal element should be what? It should be 0 only. So very important observation. For a skew-symmetric matrix, diagonal element is always going to be what? 0. Okay, non-diagonal doesn't matter, but diagonal elements are always 0. Okay, a matrix which is symmetric as well as skew-symmetric must be what kind of matrix then? Null matrix. Okay, a null matrix is both symmetric as well as skew-symmetric. Okay, so there are two theorems which we have to understand. Let me explain that. The theorem 1 says, for a square matrix A having a real number entries, A plus A dash is always symmetric and A minus A dash is always skew-symmetric. Remember this theorem, it will help us in solving some questions. If you take a random matrix A and add this with its transpose, you will always get a symmetric matrix. Okay. Similarly, if you take a matrix A and you subtract with its transpose, you will always get what? Skew-symmetric matrix. Okay. There is another theorem. The theorem says a square matrix can always be expressed as sum of the symmetric matrix as well as skew-symmetric matrix. How is it? See here. A square matrix can always be expressed as sum of a symmetric matrix and skew-symmetric matrix. How is that? Let me tell you that. So for example, a matrix A can be written as half of A plus A dash. A plus A dash is a symmetric matrix. Half of that is also symmetric matrix, which is multiplied, added with A minus A dash. So which will be giving you A itself. That means every matrix can be written as a symmetric matrix as well as skew-symmetric matrix. Every matrix, especially not every matrix, small correction, every square matrix. Only square matrix can be expressed like this. That's what the theorem says. The theorem says every square matrix can be written as sum of a symmetric matrix and a skew-symmetric matrix. Okay. Okay.